Okay, so good morning, everyone. So let's get started with the morning session. So we are starting with Nikolai Kitanine, who's going to tell us about XXX, spin chain, spinons, bound states, and form factors. Please.
Okay, so finally, I would like first to thank the organizers for inviting me here to this paradise of the hills of archery. I really like to be here, and I'll speak about some recent results obtained in collaboration with my last PhD student, Giridhar Kulkarni, about the explicit computation of the form factors for the spin chains. So what is the problem? Well, I'll start with our favorite model, XXX spin chain. Well, here the most general spin 1/2 Hamiltonian with some magnetic field, with some anisotropy parameter. But today I will restrict my consideration to the very particular case. First of all, I will do it without magnetic field. It will be crucial for our situation. It will be very important that we don't consider any external magnetic field. And today I'll speak about the isotropic case when delta equal to 1 Heisenberg chain. So the most basic example. Sometimes it's the most simple, sometimes the most difficult for different reasons. So today I will speak about this case. And what we want to do is to compute the form factors. So more or less matrix elements of the local spin operators between the eigenstates. And we consider them around the ground states. For this reason, this H equal to 0 case is quite particular. So what we are interested in FINE is zero temperature correlation functions. So we work around the ground states, and we want to compute this nice matrix elements, because after that, if you want to compute correlation functions, of course, you can proceed through sums of these form factors. So that's a very long story for the integrable QFTs. It was started by Fedor Smirnov, and then for the massive case of the XXX chain, it was considered by Kyoto group, by Jim Bemila, and also in 90s through Q-vertex operator approach. Then we wrote a paper on the algebraic Bethe ansatz approach. I will explain what is new and what we are doing now. So, well, I'd like to remind you that if you want to compute any, I don't know, time-dependent correlation function at 0 temperature, what you need is to identify some low-lying excited states, compute this form factor, and then if you know the energy momentum differences, you just make a summation. Well, we'll speak about the Heisenberg chain, which is massless model. Sometimes computing the correlation functions through the sums of form factors for massless models, it can seem to be a stupid idea, but it's not for integrable model, because integrability makes it very particular, and really already for H non-zero, it's turned out to be an excellent tool for asymptotic analysis. It's also excellent tool for numeric analysis, as was shown by Jean-Sébastien Coe. So really, we can do a lot of things if we know their form factors. So it's not a stupid idea to compute the form factors, to try to compute the dynamical correlation functions at 0 temperature through this form factor sums. So what people know to do? In fact, I'll try to explain, just it will be necessary to understand what is new in this new approach. So first of all, there is Q-vertex operator approach introduced by Jimbe and Mila, and there is lots of advantages of the computation of its. It gives you very explicit formulas. It's sort of multiple integral representations. Well, it works for massive regime for zero magnetic field, but however, it's a very powerful tool. Well, so you have explicit results. The main disadvantage that you can control well, what we like in beta ansatz picture, control of the bound states, for example, which can be seen as their complex solution of the beta equations. It's difficult to write formulas going past 4-spinon case and 4-2-spinon XXX. So there are, however, many things you can do and you cannot do. For example, well, there is a possibility to do some work also for massless XXX, but it immediately turns out completely difficult and not very natural somehow approach for the massless XXX, their Q-vertex operator approach. And there is other approach which was introduced by us in the 99 based on the algebraic beta ansatz. But well, the problem is that you write the form factors, but in terms of the beta roots. And when you go to the thermodynamic limit, number of beta roots goes to infinity. So you need to understand how they behave in the thermodynamic limit. For non-zero magnetic field, it was possible because everything was written in terms of some maybe quite unpleasant, but convergent Fredholm determinant, and the remaining part, what's called soft modes, could be summed up to compute the asymptotic of correlation function. So for H equals to, for non-zero magnetic fields, you can do it because this non-zero magnetic field plays a role of sort of cutoff in this picture. But if you go to the simplest case of zero magnetic fields, where lots of things can be computed explicitly up to a number, this method doesn't produce anything because your Fredholm determinants now are Fredholm determinants on the real axis. You don't have compact Fermi zone. Everything becomes divergent. So you have sub-zero sub-infinities in your representations. Well, you can prove some sort of, can look at it around the free fermion point, but nothing more better than that. So in fact, the case which seems to be simplest one, it's H equal to 0. We could not do it. And for example, we could not reproduce results from the Q-vertex operator approach, which was sort of strange because for the correlation function, multiple representation of correlation functions, it was one of the first things we have done. We compared two approaches. We have shown that they're equivalent. But for the form factors, it remained impossible for a very long time. And so the idea is to try to produce a algebraic beta ansatz based approach, which works in the thermodynamic limit for this particular case, H equal to 0, when there is no finite Fermi zone, and try to go to the number, just to compute form factor completely to the end without any complicated Fredholm determinant in between. So this is, so now I'll give a very quick reminder of the algebraic beta ansatz method. Even I will not go to the details. So I just need to remind you that in this algebraic beta ansatz framework, what you need is to construct an object which is called quantum monodromy matrix. And this monodromy matrix contains in the same time conserved charges, commuting conserved charges, which is called transfer matrix, which is related with the Hamiltonian by the trace identities here. So you replace more or less the problem of diagonalizing of the Hamiltonian by the problem of the diagonalizing of the transfer matrix, but also creation annihilation operators B and C. So there is this algebraic technique permitting to do this. I don't want to go into the technical details. So, and then when you know it, you can construct what is called off-shell beta states by acting of this operator B, which we used as creation operator of the simplest ferromagnetic spin states. We are in a spin 1/2 spin chain. So your reference states is all the spins up in all the sides. So you act with some B operators with some parameter lambda 1, lambda n. And in terms of these parameters, you can introduce two functions. One of this is Baxter polynomial, which is just product, the polynomial with roots in these points. and a little bit more complicated object, which is written in terms of this Baxter polynomial, which I usually call exponential counting function. So this off-shell Berta states, what is main result more or less of the 79 Fadeev, Sklein and Tartajan paper, that these states will be eigenstates provided this complex number satisfy a set of equations which can be written in this form. So if you specify this function in these roots lambda j, you obtain just -1. That's called Berta equations. And if they are satisfied for all these roots lambda j, then such states and eigenstates of the transfer matrix and hence of the Hamiltonian. So, well, that's just a small remark about the particular case of the XXX chain. Well, of course, we prove that these states are eigenstates. Question about of the completeness of the eigenstates for the XXX chain, the answer is evidently not. It's not complete because you need add some additional symmetry, but very simple symmetry, which is SU2 symmetry of the chain. So every Berta states forms a SU2 multiplet, and it depends just on the number of return spins in your Berta states. So if you have, for example, half field states, it's a singlet. If you have half field -1 is triplet, and so on and so forth. So every solution of Berta equations produce your subspace of given dimension, which is a reducible representation of SU2. And it's, of course, there is this degeneracy of the transfer matrix and of the Hamiltonian due to the symmetry. So there is this additional multiplet structure, which will be quite useful for the computation of the form factors. I just wanted to mention it here. So now what we want to do is to compute the form factors, so this matrix element between the ground state and low-lying excited states. So the next task we have is to describe what is the ground state, what are the low-lying excited states. And this is also a well-known problem solved very long time ago, even before the algebraic Berta ansatz were introduced in terms of coordinate Berta ansatz. It was description of ground states was obtained in one of the two existing Yang and Yang paper, not the third one, which was never published. But it can be shown that if there is no magnetic field, the ground state has only real solutions of Berta equations, but it fills the real line and there is no holes. So there is no real values of lambda which will satisfy also this equation. There is no some mu on this real line which will satisfy a mu plus 1 equal to 0. Such points we'll call holes in the future. So for the ground states, there is no holes. The real line is filled. There is no complex roots, and the number of Berta roots is m/2. So it's a singlet state from the point of view of SU2 symmetry. So this is, and this ground state, in fact, if you want to compute things like energy momentum for this ground state, you don't need to know all the Berta roots, all the solution of the Berta equation, which is our main point in this story. Try to do things without computing the Berta roots, this m/2 Berta roots when m goes to infinity. Because when m goes to infinity, this ground states can be described in terms of the ground state density. So more or less any sum of the Berta roots can be written in terms of the integrals with this density. Density solves an integral equation which is called Lieb equation. What is quite important, there is no first order correction because first order correction will be irresponsible for the excitations. So there is the correction starts from the 1 over m square, and this equation is well known and can be solved explicitly through the Fourier transform. So we have explicit equation, explicit expression for this ground state density. So we can explicitly compute what is ground state energy, ground state momentum. So everything about ground states is well known. Now, the next question is how to construct their excited states. And here there were many approaches. Berti himself started this story, but I will use a little bit different picture. I'll explain why. So how you do the excitations around the ground states. In fact, you can add holes, first of all, in this completely filled ground states. But when you add holes, very important, all the roots move. It's not like you just add holes in the given set of the roots and then you consider states without two solutions. No, everything moves, and even the number of vacancies will change, because number of vacancies, first of all, it can be proved, it was proved by Fadeev and Tatajan, that number of holes is always even in this situation. You cannot have situation with odd number of holes, and number of vacancies, if you produce, for example, 2 holes, becomes m over 2 plus 1. So in fact, states with 2 holes has m over 2 minus 1, not m over 2 minus 2 Berti roots. So if you just add 2 holes, you obtain a triplet with m over 2 minus 1 Berti roots. That's usually when people see it for the first time, it's sort of difficult to understand that adding holes in these Berti equations, it's even changes the number of possible vacancies. And then you have, so here I have an example with 2 holes. You can have states with 4 holes, which will be quintuplet and so on and so forth. So this will be states, simpler states where there are complex roots. But unfortunately, or maybe fortunately, because it's very interesting, in this spin chain, it's not like Lieb-Lediger. Here you can have also complex roots for the Berti equations. And here there are problems, because usually when the people consider Berti roots or complex Berti roots, they use string hypothesis. String hypothesis is something very useful when you work about the non-zero temperature. If you do things about the non-zero temperature, it works perfectly well if you work about non-zero temperature. But if you consider low-lying excitations about the ground states, that's the only case when it was more or less shown that string hypothesis is wrong. You cannot use it to describe the low-lying excitation, because there are other states which can contribute, which are not stringy states. So in fact, the proper description of this, once again, is quite an old story, but it was done by Destry and Lobenstein in '82, quite a long time ago too. They have shown how to do the description of the states around the ground states without any string hypothesis. So without making hypothesis, just trying to see what kind of complex roots can exist in Berti equation. It was more or less supported by numerical evidence. So first of all, but the first type of complex roots, however, is the same in the string hypothesis and in the Destry-Lowenstein picture, it's 2 strings. So you can add holes and you can have excitations, which are bound states with, by the way, complex roots, they come always in conjugate pair. And strings have conjugate pairs with distance exactly I. Well, not exactly, you can have some string deviation, but it's exponentially small with the size of it's decreasing exponentially rapidly with the size of the chain. So mostly this correction is really small, and we can consider this just block with a distance of I in the thermodynamic limit. So this is 2 strings. That's something which exists in both pictures, string pictures and Destry-Lowenstein picture. But then if you try to describe better that's first time of type of complex roots. Then there is what is called close pairs. Close pairs are complex roots with the imaginary part less than 1. Okay, there is always a partner, but if it's not 1/2, they've always formed a quartet. What is called quartet? Because like in the two strings, there is a partner with imaginary part different by 1 on the other sides of the real line. So such a block here, which I produced, is called a quartet, and it was proven by Destre and Loewenstein that complex roots with imaginary part less than 1 always form this configuration to be a solution of Betta equations. So that's the next type of the. So of course, closed pairs, there are 2 types of closed pairs, quartets and 2 strings, because 2 string, of course, it's from the definition that imaginary part is less than 1. For 2 string, imaginary part is 1/2, so it's also a closed pair. So in this picture, there are 2 types of closed pairs, is quartets and 2 strings. And then there is most exotic thing, it's what is called white pairs, when the imaginary part is greater than 1. So these are types of complex solution which can be realized around the ground states when the number of holes is finite, more or less. So that's, but position of this, what is important that to understand that if we can choose states with some arbitrary position of holes, it's not so about the complex roots. Complex roots defined by the positions of holes through the equations which remind a lot the Betta equations. So usually they are called high level Betta equations. So if you know the positions of holes, you can produce solutions for the complex roots. And from the position of these solutions, you just recognize them as white pairs, closed pairs, 2 strings, quartets, and so on and so forth. So, but this is really something like Betta equations on a chain of the length number of holes. By the way, number of roots in a state with NH holes, NS 2 strings, NQ quartets, NW white pairs can be always computed and given by this formula. So everything very much fixed. The positions of more or less, of course, you can consider it as Betta equations for the chain of the length number of holes. So more or less, it describes 2 power and holes states. And what is interesting, all the states will be degenerate. They will have the same energy, the same momentum. So they will describe hugely degenerate sectors in this chain with the fixed positions of holes. So that's a very important things. So more or less, when you consider this low line excitations, you replace a huge number of Betta roots, which you obtain from the solving your chain, by a finite number of Betta roots, which obtained from the higher level Betta equations. So in the future, I will speak about infinite data, the Betta roots, and finite data, the solution of this higher level Betta equations. So what we want to do, now I can precisely state what we want to do, is to express the form factor uniquely in terms of this data, positions of holes, positions of complex roots. So entirely in terms of this Betta, of the solution of these Betta equations, not in the terms of solutions of initial Betta equations. So go from this infinite data to this finite data. Goes from the infinite determinant to finite determinant. That's more or less the goal of the operations. And of course, it becomes very simple when the number of holes is small, like 2 holes. So now, sorry? No, they can be everywhere on the real line. It's just you fix the positions of holes, more or less you fix this integers because corresponded to holes, and then from this position you say, okay, we have holes in these positions, and then in terms of this position you compute all the possible states with these positions of holes, because you can have a state where just you have these holes and that's it. For example, for 4 holes you can have state with 4 holes and that's it. It will be quintuplet, so there will be 5 states like this obtained from here. Then you can have a solution with 4 holes and 1 2 strings, so 1 2 string. It will be a triplet. Then you get a solution with 4 holes and a quartet, and 4 holes and 2 2 strings, 4 holes and 1 white pairs. All this solution will be singlets. So that's quite yes, yeah. Yes, but yet here for holes everywhere, you can put it everywhere in the thermodynamic limit. So what is important, I already mentioned that all the states, all the different solution of this higher level Bernoulli equation will produce the states with the same energy, same momentum. So we know the energy, we know the momentum for the states. So if we return to the sum of a form factor, we know this exponential factor. Just we need to know to compute the form factor itself, this fz square, which was present in our sum of the form factor. This difference of energy we know, difference of momentum we know. So what remains is to compute our form factors, and that's come the new things. So first of all, we know in terms of the infinite data how to write this scalar products. It was done in our 99 paper. It can be written because of the solution of quantum inverse problem. It means expression of the local operators in terms of the generators of the transfer monodromy matrix, elements of the monodromy matrix. So in fact, everything here can be written in terms of the A, B, C, D operators, which is quite a good start. And so normalized with norms. And all these products can be written as determinants. That was the second main result of this paper of 99, using the famous Nikita Slavdov's formula of 89. Everything can be written as determinants. So, but once again, determinants which become infinite in the thermodynamic limit. So here we have Slavdov determinant, which can be written in terms of the auxiliary functions I already introduced like this. And the norm, which was computed even earlier than Slavdov formula, it's Godin formula. It's the formula for the norm of the beta states. It can be written as a this particular nice defined determinant. So, but this is complicated thing because it contains infinite number. It depends on all the Bernoulli parameters for the graph for the excited state. So what we want is to reduce it a little bit, and it looks like so. Then we can, by the way, just I would like to mention that here for the XXX, we need some modification of Slavdov formula, which was obtained by Omar Ford and Michael Wheeler in 2012. And in fact, this generalization of, I should thank the Galileo Galilei, because this formula was made by Ford here. And well, so yes, and so but that's a modification of the Slavnov matrix, which works for this multiplets, and we need it here. But okay, then what we try to do is quite a stupid thing. We have a ratio of 2 determinants, Slavnov determinant divided by Godet determinant. So we try to divide matrix by matrix. And I don't know why nobody did it before, in fact, because you just write this Godet matrix, or this Slavnov matrix divided by Godet matrix, more or less, you reduce it to a set of linear equations to obtain this resultant matrix. What is nice, a set of linear equations already for the finite size can be written as in a residue form because you sum of the solution of Bethe equation, which is given by this denominator. So you can write this just integral using residue theorem. And there is some poles, other poles you can take into account, which sort of simplify your right-hand side, which permits you in the thermodynamic limits, some part of this contour, in this case, goes to 0, and the equation becomes very simple. Maybe you recognize the Lieb equation I have written in the beginning. No, here I consider them in the bulk, on the contrary. The position of the holes here is up to now we're speaking about the ground states. So everything in this G is the ground states, but then we go to the second determinant, which is dependent on position of holes. And yes, that's quite important. We consider in the bulk, they're not very close to the, because otherwise the second part of the integral will be quite difficult to estimate. And that's open questions how it behaves if there is some extra correction appearing if it's close to the tails. But here we consider the bulk case. And in the bulk, you solve this equation, you obtain very simple expression for your results matrix. And that's a Cauchy matrix, something you can compute. So I skipped, of course, the technical detail here, but more or less from the ratio of two complicated matrices, you obtain a very simple matrix, which is Cauchy matrix. That's a little bit more difficult for the, more complicated for the second determinant, because second determinant you consider as the Slavnov formula. It's a scalar product of a Bethe states with some arbitrary state of shell Bethe states. So in first determinant, you should consider as a Bethe state the ground states, and that's more or less simple. And in the second formula, you should consider the Bethe state, the excited states. It becomes more complicated. You have once again the Cauchy matrix. Oh, sorry. Once again the Cauchy matrix, but it's sort of perturbed by finite rank matrix. So if you get out your Cauchy determinant, and what is great about Cauchy determinant, you can not only compute the determinant, but also compute the inverse matrix easily, analytically. You obtain just a perturbation with finite size determinant. You obtain just a finite size determinant. So that's what's the goal of the operation. We get from the infinite determinants to the finite determinant, and we get to something very simple because so we have. Well, in fact, there is some difficulty in the first determinant too if there are if there are complex roots. So more or less, once again, there is some perturbation of finite rank. And this rank is number of complex roots, what we call number of complex roots, because and from the second determinant, we have a perturbation of finite rank with the size number of holes. And otherwise, it's a product of well-known quantity you can express in the thermodynamic limit just in terms of the density of roots. So all these prefactors, they can be computed in the thermodynamic limit, and what is remained is just finite size determinant. So this is the main. So let's consider the simplest, really the simplest excited states. Two holes, and that's it. Then you cannot have complex roots because if you add, you can add two strings, but then you obtain singlet state, and it's easy to prove that for singlets, all the form factors are 0. So the non-zero form factor you obtain only for triplet states. So here there is no there is no complex root. So here you have just one, and second matrix is just 2 by 2. And it can be explicitly computed. And we obtain the result for the 2-point form factor. So as I told you, up to a number. So it will be just a product of Barnes functions, something really very simple in terms of the positions of holes. So really the formula is extremely simple. This is not a new result. This results a little bit for us to see that the method works. Leads because from the Q-vertex operator approach, the same results were obtained either, well, in a little bit different form. You can prove that these two formulas are equivalent, but more or less it was already done. So, but starting from 4 spinon case, we have complex roots, and more or less complex root is something which don't appear in the Q-vertex operator approach. So that we go to this, but the general results anyway, it's very sort of finite results. I just put it as general formula. So you have the same factor we have in 2 spinon case. So it's just a scattering factor of 2 spinons, 2 holes. But of course, you have product of the scattering for every pair of holes. So this is obtained explicitly from this huge product, huge product here, and Cauchy determinant. In fact, it comes out from this Cauchy determinant, and there remains this 2 determinant, this finite size determinant. So I remind you that there is number of holes, and this determinant of number of holes. This determinant is what we call number of complex roots. So it's number of strings with twice number of quartets with plus twice number of white pairs. Don't ask why. It's the structure of it's to how many holes corresponds every type of the complex roots. So, but this are finite size determinant. Well, inside this determinant, I did not put here because the entries of this determinant depend on the type of roots and type of complex roots we have, and they include some integrals with some auxiliary function, but everything is explicit. But well, to tell you the truth, the current form of this determinant, even it's explicit in terms of position of holes, position of complex roots, but I don't like it. I'm sure that there is a simpler one. So this is work in progress. We try to get a simpler, but it's implicit result only in terms of these holes and complex roots. And what is nice also that inside of one of the determinant, we have something like higher level Godin matrix. So something like norm of beta states from the higher level beta equations. And also, so it's very explicit results only in terms of this finite data. So that's more or less the goal. Well, I would like to simplify it a bit because expressions for this determinant now, they're quite complicated, but I'm sure that it's possible, but that's a work in progress. But anyway, what is done is we have everything in terms of this finite data now. So that's something we know how to do. What would be interesting to see, because very similar thing can be done from the fermionic approach by Smirnov, Jimbe, and Biva. They also see a little way how to go from the quantum field theory more or less to the spin chains and to write equations for the, it's possible to write some equations for the form factors in this Destri-Lowenstein approach. So correspondence between these two picture is not clear for me yet, and it's very, very interesting questions. What are the correspondent of what we do straightforwardly from the existing determinant representation to their nice fermionic approach. That's a big open question. So another thing what I like to see in this story is how to look at it when the number of holes becomes bigger and bigger when you go far from the ground states and you obtain some non-trivial overlaps. Because what we have done here, we had some, in the Slavnov formula, some densifications of beta roots, which produced us some simplifications, some determinants we can compute. And so if we do some second densifications, if we densificate the holes, if we go to the, then it will be possible, I think, to go to the finite temperature, to go to some non-trivial overlaps for the some I don't know, out of equilibrium problems. For me, it's interesting. If for this reason, I want to simplify this to determinants, because how to see how it behaves with the number of excitations becomes again infinite. So, but up to now, and I hope that there will be some clear algebraic structure which will come out, something like maybe like higher level Slavnov formulas, higher level Godet formulas already appeared. So I hope that there is some easily identifiable algebraic structure related with this higher level Bernoulli equations. So for me, the most interesting question, how this higher level Bernoulli equations play out in this new determinant formula with finite data. So that's, I thank you for your attention.
Thanks a lot for the talk. Any questions?
It seems that the magic comes from the fact that you can take the ratio between determinants. Yes. So is that just an accident in your opinion, or it can be generalized to other correlation functions?
I think it's not an accident. I think it's something which is deeply encoded in the structure of the Godet determinant that it can be taken out, in fact. So that's a very nice property of the Godet determinant which was not used before. I hope so. I hope so. But well, I don't know yet, but I hope so. I hope that that's something which should be used. In fact, that is something really nice property of the Godet matrix which was not used before.
Yeah. So first, like technical question, shouldn't be here like m to the power 2 and h? Because then you have to sum over all positions.
At h, no, it's wait.
But let's
yes, 2 at h. Yes, you're right.
Okay, and then
at h, of course.
Yeah, but then you have to sum over all positions
of holes. Yeah.
Yes, and then you have 2 holes and only one over m.
For example, that it's if you have 2 holes, it's m power 2.
Okay. So then question
is even. And h is even. That's a little bit. Sometimes we write NH.
And h is even. Oh, I see.
Even.
I see. Good.
It's all. There is a yes. There is a always some
right,
problem
so
of notation. Sometimes NH, it's written
I see.
But to underline the fact.
But question is, so for instance, what JS did, he resummed like 2 spinon, 4 spinon.
Exactly.
So my question is here. Let's fix NH like simplest. Let's say 2.
Yes.
And then just perform summation of this.
Well, it's what here we just reproduce the result used by JS in his summation of 2 spinon. It will be the same.
Yeah, but in your case it will be just analytical because it will be just like 2 integrals, right?
Well, but he used Jibba result in his paper. In fact, he used this result I mentioned by Bugurzi, Couture, Kashir at some moment. So it's in fact, at some moment in the beginning he used for XXX. In the beginning he used this big determinant, but then he compared it with this explicit result.
I see.
He only did it through Abacus. He did it in different ways. So this was already used by JS to sum up that.
I see. Okay, yeah. Because then the question would be, can you reproduce this, well, even in static case, one of square root of x behavior, if you just take like 2 holes, because it will be some function of x.
Well,
so the question,
we need to look at the more or less mathematical. Well, we can do it in the hooligan way, just to take the limit and try to see. But mathematically, it's a little bit complicated because to control things when you send holes to infinity here in this approach, there are some subtlety, and I'm quite prudent not to do it in a straightforward way. Just send it and see what it gives, because it's it can produce correction. Well, probably it's the right way to do, but I cannot prove that it's
but it's just interesting what function of x.
Yeah. So here, to be prudent, we say that all the holes are in the bulk, not in the tails of the distribution.
Okay. Yeah. Thanks.
Okay, any further questions?
So can you comment if you want on the possibility to calculate the edge exponents using your methods, if it's
Sorry?
edge exponents, the edge singularities?
Edge exponents.
Can you do this using like 2 holes or like 4 holes?
The answer is I don't know. In fact, it would be nice to try, but I'm not sure that this really, well, and probably for h equal to 0, it can be done with without any without this soft mode summation we have done for h not 0, and just 2 whole states can be used to do it. I think yes. I think that, but I'm not sure. But I think yeah, that you just can do it from the low level excitation, but it's not done yet. Yes. Yes, I think it can be done, but it's not done yet. So it's one of the open questions here. Yeah.
Any further questions? Okay, if not, let's thank Nikolai.